Hey folks, let's see. We are starting off our unit on exponential and logarithmic functions. Today we're going to be talking specifically about exponential functions. So I've got three questions here I want you to think about, and go ahead and pause it and see if you can come up with answers to these three questions, and then continue and listen to my explanation. So pause and continue. So, question number one. What is the general shape of an exponential function? Well, generally speaking, an exponential function is going to look something like this. It's going to start down and to the left and go up and to the right. It's going to keep on increasing forever, and to the left, it's going to get closer and closer and closer and closer to zero, but it's never quite going to touch it. It will have the equation like y equals 2 to the x, or maybe 3 to the x. 3 to the x would look like this, but it would be steeper. Or maybe it's y equals 4 to the x, and it's again pretty similar, but even steeper yet. But they're all going to have that same general shape, and more importantly, they're all going to share this y-intercept, because the y-intercept occurs when you plug in 0 for x. And think about what happens if you plug in 0 for x. Well, in the bottom function, we're going to get y equals 4 to the power of 0. Well, 4 to the power of 0 is 1. And in the other function, y equals 2 to the power of x, you're going to get 2 to the power of 0, which is also 1. Anything to the power of 0 equals 1. Hence, all of these functions, assuming they have not been shifted up or down or side to side, they will have a y-intercept of 1, just like that. Question number 2 is claiming that f of x equals 2 to the power of negative x is the same as g of x equals 1/2 to the power of x, and we want to show that that's true. There are a couple different ways to do this. Let's start with f of x. So let's say f of x, equals 2 to the power of negative x. And let's use some exponent rules to rewrite this. Well, first off, you can think of this as 2 to the power of negative 1 times x, because we all know that if there's nothing in front of the x other than negative, there's really a little 1 there. That was a weird way of saying that, but we can always throw that coefficient of 1 out front. Does not change anything. And now we have another rule of exponents that say that is exactly the same as that. And now think about what we can do with negative exponents. Well, I can rewrite 2 to the negative first as 1 over 2 to the first. That's to the power of x. So you see we get 1/2 to the power of x, which is our g of x function. Bada boom, bada bing. And you could take that in the opposite direction to start with g of x and get to f of x. Question number 3, will the function f of x equals a to the x plus k have a vertical or a horizontal asymptote? If so, where and how do you know? So, firstly, remember what we talked about with problem number 1. All these functions that are f of x equals a of x, like that, well, they're all going to look something like that, unless a, of course, is a fraction, in which case it's going to flip it across the y-axis, or unless, yeah, well, that's good enough. Okay, so they're all going to look like that, and they're all going to start with that y-intercept right there at the point 0, comma 1, because a to the 0 is 1. But here's the deal. We have this plus k right here, which is going to shift your graph up by k. So normally this function has a horizontal asymptote all along the x-axis. As the x values get smaller and smaller, smaller, more negative, your function gets closer and closer to 0, but never quite is 0. And so we end up with that horizontal asymptote there. Now it may look like we have a vertical asymptote there, but we absolutely do not. Think about it this way. You could continue to plug in larger and larger x values, so your graph would move to the right, and you would continue to get larger and larger y values. So your graph's going to keep on going up forever. It's just going to start doing it incredibly steeply. So what was I saying? We don't have a vertical asymptote, but we do have this horizontal asymptote here. And if you shift everything up by k, well, guess what? The horizontal asymptote will also be shifted up by k. So we're going to end up with something like this, where I did have a horizontal asymptote at the y value of 0, and I now have a horizontal asymptote at the y value of k. But even deeper than that, I did have my y-intercept at the point 0, 1, which I have written there as well. But now I have my y-intercept at the point 0, k plus 1, because I have shifted everything up by k. So those 2 points move as such. So if I think of a function y equals 2 to the power of x minus 4, well, I know it's going to be a 2 to the x function, so it's going to look something like that, except, however, it's shifted down 4. So I'm going to go 1, 2, 3, 4. I'm going to move my asymptote down there. I know that my function is going to cross the y-axis 1 point above that asymptote, and once I have that, then I will sketch in my graph, and I'm looking pretty good. So these are our goals for the day. We want to create some quick sketches of exponential functions. We want to then use an exponential function to model some sort of growth. So let's get straight into it. Let's sketch the graph of y equals 2x, showing its y-intercept. Well, we already did this in the previous problem. What we know is we have the y-intercept there at 1. We know it levels out to the left and shoots off towards infinity to the right. But we want to state the domain and range. And so the domain is going to be all real numbers because I can plug any x value into it that I want to. And my range is going to be all real values, all real numbers that are greater than 0. Because again, I have a horizontal asymptote at y equals 0. I will never quite touch it. And I go up to the right, so I can go up to positive infinity. So you could say it like this, or you could say 0, positive infinity, but you have to use brackets like that. And when I say brackets, I mean not brackets, I mean parentheses. You have to use parentheses because it never quite touches 0, and it never quite touches infinity. So now we're going to start graphing some transformations of this mother function, but I don't want to plot points every single time. I want to use this general shape of an exponential function, and I want to use that as the mother function and then apply transformations to it. So just like when we're graphing parabolas, we can use the vertex kind of as an identifying point. I want you to treat the y-intercept of the mother function kind of like the vertex of a parabola, by which I mean I want you to track where it goes. I'll show you what I mean in a moment, and by in a moment I mean how about now. So if we have the graph of y equals 2 to the x plus 3, how do we graph it? What does it look like? And where did the y-intercept and horizontal asymptotes move to? So again, we're going to be comparing it to the mother function of y equals 2 to the x, which has a y-intercept of 0, 1, and a horizontal asymptote along the line y equals 0. And I wrote 2x when I meant to write 2 to the power of x. So this is going to be our base for comparison throughout these problems. Now let's think about what this new graph is going to look like. So 2 to the x plus 3, so it's going to be this green graph we have, except it's going to be shifted up 3. So that y-intercept there at 0, 1, well, that's now going to be at 0, 4. And that asymptote that was along the line y equals 0, that is now along the line y equals 3. Everything on this graph, every single feature of this graph is going to be shifted up by 3, including y-intercepts and horizontal asymptotes. So now let's look at this function, y equals 2 to the power of x minus 4. Well, remember what happens when you subtract or add something to your exponent there. It gets translated to the left or the right. When you subtract 4, it moves to the right. If you were to add 4, it would move to the left 4. So we're going to take that y-intercept there, and we are going to move it to the right 4. And another way to think about that is that y-intercept, that y value of 1, that is going to occur when that exponent, x minus 4, is equal to 0. Well, when is x minus 4 equal to 0? When x is 4, because 4 minus 4 is equal to 0. So that point gets shifted over 1, 2, 3, 4, and so now I know I have that point right there. Since all we did was translate it to the right, the horizontal asymptote does not change. That is still along the line y equals 0, but that point right there is now along the coordinates of 4, 1. And that's what I mean by tracking that point. We want to know where does that shift, because showing me that point on there shows me that you know what this transformation is doing. Let's take it one step farther. What if we wanted to know where the y-intercept of this function was? Well, we would have to plug in 0. So we get y equals 2 times 0. It's 2 to the power of 0 minus 4. Well, 0 minus 4 is 2 to the power of negative 4. And 2 to the power of negative 4 is 1 over 2 to the power of 4. And so we get the teeny tiny fraction 1/16. And now we know that that is the point 0, 1/16. Alright, another transformation of the mother function y equals 2 to the power of x here. I now have y equals 2 to the power of negative x plus 2. So I'm going to think of this bit by bit. First off, I'm going to think of what does 2 to the negative x do? Well, when you throw a negative in front of your exponent, you create a reflection across the y-axis. A reflection in the y-axis is how it's more commonly referred to. So we're going to get the same graph except a perfect mirror image of it. So it's going to look like that instead of going like that. And so that's what that transformation does, but we also have the plus 2, which is going to shift everything up 2. So I know my y-intercept is going to be up here at the point 0, 3, and I know that my horizontal asymptote is shifted up 2, so I get that. So I can sketch it in just like that. So again, it helps to think of these transformations as a series of transformations. Just make sure you follow order of operations. Y equals negative 2 to the power of negative x plus 2. First off, this is pretty similar to the last one. Notice the only difference is I have a negative out front. Now, don't be confused here. You need to think of this as 2 to the power of negative x with a negative out front. Order of operations says exponents before multiplication. That negative out front is really like negative 1 times 2 to the power of negative x. So you have to do that 2 to the power of negative x first. Otherwise, you'll end up with a crazy graph that looks like that on your calculator. So again, let's think of this in bits and pieces. So bit and piece number 1 is the graph we created last time, the 2 to the negative x part. Well, I know that that's going to look like that, and that's going to have a y value of 1 right there. Now think about then what happens if I make that negative. It's going to be a flip of this entire graph over the x-axis, so it's going to look like that. And that's going to happen at negative 1 instead. And now that we've done both of those pieces, let's add 2 to everything. And so I'm going to take this purple graph and shift it up to get, let's change my color. How about blue? But how about a fun blue? Let's now shift everything up 2. So I'm going to end up with that original y-intercept, but now my graph is going to be looking like that. And let's think about the horizontal asymptote. It's going to happen one above it right there. So see how that's all pieced together. We go from the original green over here, and then we throw that negative in front of the x so it flips it to the second green graph over here. And then we go ahead and do that negative out front so it flips it down to the pink graph. And then finally we add 2 to it and it shifts that pink graph up by 2. And so all that stuff moves along with it. So here's another idea. We want to sketch all these graphs here. We kind of already talked about it, but let's go y equals 2 to the power of x. That's going to look something like that with a y-intercept of 1. And then let's go y equals 3 to the power of x. It's going to look very similar, except it's going to come in a little more abruptly and rise a little more steeply, but still going to have the same horizontal asymptote, still going to have the same y-intercept right there. And finally, let's look at h of x equals 5 to the power of x. Same idea, except it's going to start even later, rise more steeply like that. But each time, you're just going to get a modified version of the same thing. They're all going to have the same y-intercept of 1 right there, but they're going to grow at different rates. So let's now apply what we've just worked through and sketch these three graphs. So let's start off with f of x. That's a good place to start. So negative 3x minus 2. So take it piece by piece. First thing, I'm not going to freak out about the fact that the base is 3 and not 2 or not 4 or not 8. I'm just going to acknowledge again that that's just going to dictate how quickly my thing is going to rise. So it's all going to be the general shape, so I just want to think about the other transformations. So first off, remember that the negative out front means that it is going to, instead of being up like that, it is going to be down like that. And then the minus 2 is going to shift everything down by 2. So currently, my horizontal asymptote would be at y equals 0. So now it's going to move down to y equals 2. That y-intercept was at negative 1. So now it's going to be moving down to negative 3. So let's sketch that all in this big graph. So my y-intercept moved down to negative 2. So I get that. Meant to say horizontal asymptote there. My y-intercept got shifted down to negative 3. So I get that right there. And I've got that negative out front, which is flipping my graph down. So I'm going to get that little feller right there. Let's talk about domain and range of this function. Well, my domain is all real numbers because you can plug any x number you like into this function. And my range is going to be, let's do the fancy version. First off, that was terrible. Let's redraw that bracket. Let's go y is an element of the set of all real numbers such that y is less than negative 2. And again, we're just saying all the y values below negative 2. So I could also write that as negative 2, comma, infinity. And that's totally not what my brain meant to tell you. My brain meant to tell you negative infinity to negative 2, because you want to put the lower value on the left and the higher value on the right. So there you have it. That is f of x. Let's do g of x now. All right, g of x is going to be a fun journey. So let's sketch this graph real quick, and let's acknowledge that the 1/4 is the same as, again, you can think of it as 4 to the negative first. And so that's really what I have going on here. And so you can think of it like this, and then we could rewrite this as 4 to the negative x minus 2. Distribute that negative in. And if you remember back to Unit 1, when we dealt with weird things like this, where we had negative x plus 3, if that negative was inside there with that x, it changed how your horizontal translation worked. If you had that negative there, normally we think, oh, since it's x plus 3, that plus 3 moves it to the left. But here, we're going to actually end up with that plus 3 moving it to the right. Because again, you got to think of it in terms of, well, what makes this stuff 0? And, well, plugging in a 3 makes it 0. So in this case, the plus 3 shifts it to the right. So up here, when we're graphing this, that minus 2 that it's become is actually shifting it to the left. So think of the 4 to the negative x. That bit right there is going to make it so that it goes up and to the left. And then the minus 2 is going to shift it to the left too. So over here, I know that that value, that y-intercept there, that's normally right there, is going to be moved over to the left too. So it's going to go to that point. And I know my graphs, whoa, that was bad, let's redraw that. It's going to go down like that and up like that. So another way to think of it without doing that crazy exponent stuff that we did, think of it as we've got the x plus 2 transformation, which we know is going to shift it left 2. And then we got to think about the 1/4 is the same as x to the negative 4th, which opens up to the left. And so with that similar logic, we get the same graph. So let's now look at h of x. h of x is 2 to the power of negative x plus 3. I think, did I write that down correctly? Yeah, 2 to the negative x plus 3. So we want to, again, sketch this graph. So acknowledge that the negative x is going to flip it horizontally. So we're going to be looking like that. And the plus 3 is going to shift it to the right 3. Because, again, we're thinking about where does that point go? Well, that point goes wherever negative x plus 3 equals 0 at, and that happens when x is 3. So we're going to get 1, 2, 3 to get that point right there, and it's going to be going up and to the left, and so our graph is going to look like that. And again, if we wanted to know the exact value of that y-intercept, we could plug in 0 for x, and we would get 2 to the 0 plus 3, which is 2 cubed, which is 8. So I know that that y-intercept right there is the point 0, comma 8. And again, if you want to think of it in another way, h of x equals 2 to the negative x plus 3. Well, let's factor out that negative x and make it 2 to the negative 1 times x minus 3, because then I can rewrite this as 2 to the negative 1 to the power of x minus 3, and I can finally rewrite that as 1/2 to the power of x minus 3. So then when we have our positive coefficient, we see we get x minus 3, which shifts the graph to the right as we can normally think about it. And also we get that 1/2 there, which reflects it in the y-axis. So we got a little bit of a situation here. Topanga's grandmother, lovely lady, decided to give Topanga $150 on her birthday. And to encourage Topanga to be a responsible young woman, her mother decided to offer her this deal. She said, "Topanga, dear, if you save that money and put it in a piggy bank, I will give you an additional 12% on the amount currently in the piggy bank at the end of each year." So let's think about how this is going to work. So let's make a little column here. Let's say T for the number of years. And then over here, let's talk about the amount of money that Topanga has. So at T0, aka before she starts this little mom program, she has $150, the original amount that her grandmother gave her. But then what happens at the end of year one? At the end of year one, she still has that $150 that her grandmother gave her, but now she has the additional 12% earned on that $150, which we can calculate by taking 150 and multiplying it by 0.12 to figure out 12% of 150 and add that to the original cost. But think about what we can do. both of those terms, 150 and the 150 times zero point 0.2, both of those terms have a 150 in them, so I can factor that 150 out. And what am I left behind with? Well, I'm left with 1 plus the 0.12. Check yourself if I wanted to distribute that back in and see that I would get right back to where I was right there. So I'm going to simplify this one step further and call this 150 times 1.12. And again, you've probably used this before when figuring out how to tip a waiter or something like that. The one part of that 1.12 says keep the original 150, and the 0.12 is saying add 12% on top of it. So let's go ahead and calculate that number. That number is going to be $168. So after 1 year, she gets $18 from her mom just for not spending that initial amount of money. And then what happens after, say, 2 years? Well, after 2 years, she's going to again follow the same routine. She's going to take the amount she currently has, which is $168, and she's going to add to that she's going to add to that 12%, so 168 times that 0.12. I can't write, and I'm getting goofy parentheses. But now I'm going to get super fancy with it, because let's recognize that 150 times 0.12 is one way to write 168. That's what that says right there. That's what equals means. So I'm going to rewrite this as, instead of 168, I'm going to write that first 168. Actually, no, let's do this first. First, I'm going to factor that 168 out of each of these terms to get 168 times 1 plus 0.12. And then, again, I'm going to recognize that 1 plus 0.12 is the same as 1.12, and now I'm going to rewrite that 168 as 150 times 1.12 from right here, bringing that down, and then I still have that 1.12, so I really get 150 times 1.12 squared. Interesting. So now let's do one more. Let's do t equals 3 years. So again, I'm going to take the previous amount that I got. So I forgot to tell you that before, but that should be 188.16. So now let's say we're starting with 188.16, and we're going to add to that again that 188.16 times the 0.12, which is 12% of what is currently in there. That's what we're increasing the amount by, which is again 1.0. Messed that up. I meant to write 188.16 times, factoring it out, we get 1 plus 0.12, which is again 188.16 times 1.12, and now I'm going to use that same little rewriting trick as last time. I know that 188.16 is the same as 150 to the power times 1.12 to the power of 2. So I'm going to write this as 150 times 1.12 to the power of 2, but then I still have that 1.12 being multiplied right there. So this will simplify to 150 times 1.12 to the power of not 2, but 3. It's going to be absorbed, and we can plug that into our calculator, and you will get $210, $210.74. So after 3 years, she has increased the amount of money she has by a lot, a significant amount. So go Topanga. Congratulations to you for saving your money. So now then, what if we want to know how much money she'll have after an arbitrary number of years, aka how do we write an equation to model this? So remember, we started with 150, and then after the first year, we ended up with that original 150 times 1.12, which was some number. And then in our second year, we ended up with 150 times 1.12 squared. And then the third year, 150 times 1.12 cubed. And so in the teeth year, we're going to have 150 times 1.12 to the power of t. And we can break this down more generally. We can say that after t years, you will have your initial investment, in this case our $150, times 1 plus your annual rate of interest to the power of t, the number of years. And we get that little general equation right there, and it looks beautiful, and we can say that that is a of t, the amount of money with respect to time. So again, we get the amount of money with respect to time. So the amount after t years is equal to the principal investment, aka the amount of money you start with, times 1 plus that annual rate, all raised to the power of t years. And we can generalize this even farther by looking at situations where your money is compounded not necessarily annually, once a year, but perhaps maybe monthly, so 12 times a year, or say weekly, so 52 times a year, something like that. The equation is almost the exact same. Look at how similar it is to that. The only difference is we now have our rate divided by n, the number of compoundings per year, and we also have n times our time, t, the number of years, which is going to tell us the total number of compoundings. So if it's the same annual rate, you have to split it up to figure out how much you're getting each month, and then it is compounded an additional number of times, so you have to multiply the time by that number of compoundings. And so let's apply this to the problem here and figure out how much Topanga would have after 3 years if her mom compounded her interest monthly. So originally, after 3 years, with just the annual compoundings, she ended up with $210.74 after 3 years when her money was compounded yearly. But what if that money was compounded monthly, for example? So to figure that out, we need to use this equation. A of t equals the principal amount, which is 150, times 1 plus our rate, which is still our annual rate, which is still 0.12, divided by the number of times it is being compounded. It is being compounded monthly, so we're dividing it by 12 because there are 12 months in the year, multiplied by our number of compoundings, which is again 12, times our time, which is 3 years. So let's think about what this is going to give us. Well, we can simplify this as 150 times 1 plus 0.12 divided by 12. It's going to give us 0.01, which is telling me that if I am getting 12% interest per year, I'm getting 1% interest each month. And then I'm going to multiply that by 36, which is the number of months in 3 years. So do that, and you should get. So if she compounds monthly instead of yearly, she's going to end up with about $4 more, which doesn't sound like much more, but like that's pretty cool, and that's only on $150. Imagine if it was on like, I don't know, like $30,000 or something like that. Whoa. But let's now compare that to what would happen if it were compounded weekly. So we're going to do the same thing. We're going to say that the amount, and I should say 3 there. So the amount after 3 years is equal to the initial deposit, $150, times 1 plus our rate, our yearly rate, 0.12, divided by the number of compoundings. And if we're doing it weekly, we're going to be doing it 52 times, because I'm pretty sure there are 52 weeks in a year. And this is kind of pathetic, but after I just said that, I started to second guess myself, and I was like, oh my gosh, I need to actually Google this now. And I typed in number of weeks in a year into Google, which I'm, again, kind of sad that I did, but I did, and it came up with a lovely, lovely little calculator here. And it says that there are actually 52.1775 weeks in a year, which is just unbelievably frustrating to the mind. So anyways, we're going to use 52 and not 52.1775, but we're now going to multiply that by 52 times 3. And again, we can simplify all this. And so again, we can simplify the insides there. The 0.12 divided by the 52 is saying if you have 12% per year and you're using part of it each month, split it up evenly, you're going to get 0.00231, which is saying 0.231% each week. And then the 156 is the number of weeks in 3 years, and multiply all that together and you will get 214.99. So not as drastic as an increase from the yearly to the monthly as it is from the monthly to the weekly. Notice we only went up by about 37 cents this time, but still a little bit better. So what if we do it daily? Well, same exact setup, except now do it with 365 instead. And yes, you don't need to ask, I did change the units on the Google Translator from weeks to days. There are 365.242 days in a year. So again, I'm going to go A of 3 years equals 150 times 1 plus 0.12 divided by 365 times 365 times 3, and you will get. Hey guys, quick correction. I apparently can't do math. This number right here shouldn't be 99 cents. That should be 92 cents. Because then when you go through and compound it daily, you end up with this little feller right here. You get 214.98 that way. And I knew that that couldn't be less than the other one. So again, interesting. It increases rapidly at first as you increase the number of compoundings, but then as you can continue to increase the number of compoundings, the amount that it goes up starts to slow down. That's pretty weird, and it makes me wonder out if it eventually it levels out, which makes me wonder, does the limit as the number of compoundings increases get you somewhere interesting? I probably just sounded really pompous when I said that. I just went back and listened to it, and not only do I sound pompous, it's like I didn't even say the sentence properly. I was trying to ask, do you think as we increase the number of compoundings per year indefinitely, aka the limit on the number of compoundings per year as that goes to infinity, it seems like this is leveling out to some number, and the question is, what number is that? Well, that's for another day.